Okay, we're going to look at the Jovian moons of Jupiter, Saturn, Uranus, and Neptune. Here's some general information. There are about 164 known Jovian moons. Actually, that number seems to be changing from day to day, so that's the most updated version. We attribute maybe about 62, possibly 63 to Jupiter, another 62 to Saturn, about half that, 27 to Uranus, and maybe about half of that, 13 to Neptune, giving us about 164 moons. The 6 largest Jovian moons have planetary features, and 3 of these moons are studied by exobiologists. An exobiologist is a biologist who is looking for features and environments that would be conducive to life beyond our own planet. So exo meaning beyond. And these moons are Jupiter's Europa and Saturn's Titan and Saturn's Enceladus. Europa and Enceladus having the possibility of liquid water somewhere underneath the ice crust, and Titan having an atmosphere similar to a primordial Earth. Pluto is no longer a planet. It's more moon-like than planet-like, and hence it would be more like one of the larger Jovian moons, like Triton. Here's a quick look at some of these major moons in the solar system. You've got the Earth in comparison here and Earth's moon in comparison. You have the 4 Galilean moons down here of Jupiter, and you can see how they relate to Earth's moon in size, Europa being slightly smaller. Then you have some of the Saturnian moons over here in this corner, Titan being the largest, and that's almost on the size of Ganymede. And then you have some of the medium-sized moons of Saturn. You have Uranus's moons over here, Titania, Miranda, Oberon, they're just medium size. Then you have Triton, which is Neptune's largest moon. And you have Charon, which is the moon of Pluto, which is not really a Jovian moon anymore, so we could cross that one out. Here's a comparison of these 6 largest Jovian moons to our moon. Our moon's relative distance and orbital period is much larger than the large Jovian moons because the large Jovian moons are going around larger planets. And our moon is relatively far away in relation to the planet, 60 Earth radii away from the Earth, taking 27.3 Earth days to go around the Earth. In comparison, the large Jovian moons are much closer to the parent planet in terms of the radii of the planets. The first 3 Galilean moons have a 1 to 2 to 4 period ratio. In other words, Io takes 1.77 Earth days to go around Jupiter, and almost exactly twice that, Europa goes around in 3.55 days, and almost exactly twice that, Ganymede goes around in 7.15 days. So it's a 1 to 2 to 4, and you can even extend this possibly to Callisto being almost exactly twice that, to 7.15 Earth days going around Jupiter. So if you were to observe Jupiter over a week's period, you could clearly see these moons in their orbit about Jupiter. Neptune's Triton orbits retrograde, which gives it a negative Earth period, and that's probably the most convincing evidence that is indeed a captured Kuiper Belt object instead of a moon formed along with Neptune itself. Here's a comparison of size. In terms of the Galilean moons, largest density is Io, and then it gets less dense as you move further away from the Jupiter in order: Io, Europa, Ganymede, and Callisto. Io being upon the same density of our own moon. Titan and Triton being just about twice the density of water as is Ganymede and Callisto, suggesting that maybe water and dirt are their major contributions to their density. Sizes of Io and Europa are similar to our own moon, and the sizes of the three largest Galilean moons, three largest Jovian moons, two of them Galilean, Ganymede and Callisto, and Saturn's Titan, are similar in size to the planet Mercury. And if you compare Triton to Pluto, they're about the same size and same density as well, suggesting that maybe both of those came from the Kuiper Belt that's nearby. Here's a comparison of two of Jupiter's moons, Io and Amalthea, and we can see that Io, being a Galilean moon, is much larger than Amalthea, but Amalthea is still a Jovian moon, not still a Jupiter moon. So at some point you have to decide what's actually a moon and what's actually just a big rock going around the planet. Jupiter has 62 known moons. Most of these moons are small, like Amalthea. If we were to compare the mass of Jupiter's moons, we'd see that the four Galilean moons take up most of the mass of the Jupiter subsystem. Io being blue here, Europa this reddish color, Ganymede green, Callisto purple, and all. It's kind of hard to see on this pie chart, but all other moons are this lighter blue, which I believe is this little slice right here. So as we look at that little slice, we can see that the other 58 moons of Jupiter just fit in that little mass right there, and the four Galilean moons comprise most of the mass of the Jupiter system. Here's a neat look. If you were to look at Jupiter through a good amateur telescope, you might be able to see something like this. Jupiter with its band structure and the four Galilean moons. And probably what you'd want to do if Jupiter was prominent in your sky is to look at it day by day and watch these moons move and change their position in relation to Jupiter. That'd be a neat sight. Here are the four Galilean moons up close and personal to each other, compared. They were discovered by Galileo in 1609 when he first started using the telescope. They're named after the mythical conquest of the Roman god Jupiter. And they are all spherical. They decrease in density with their distance from Jupiter. So Io being the densest, Europa, Ganymede, and Callisto following after that. Io being greater in density than our own moon. Io and Europa are similar to our moon in size. Here's our moon. So Io is probably a little bit bigger and more massive than our moon slightly. Europa's a little bit smaller and less dense. And Ganymede and Callisto are similar to the planet Mercury in size. Very interesting. Mercury being a lot denser than these two spheres. Here's Io and Europa against the planet Jupiter, and very interesting comparison. Taken by Voyager 1. As mentioned, there's this curious solar system of Jupiter with the 4 Galilean moons. They're all going circular orbits in a prograde direction, the same direction as the planets around the Sun. They're all tidally fixed in the equatorial plane of Jupiter. Density decreases with distance, and they have this 1 to 2 to 4, possibly to 8 resonance of time in which they go around the planet. And as said before, that is just too unusual to be a coincidence. That would be something for a prominent astronomer to figure out why that would occur. In fact, if you figured out why that occurred, probably would be worth a PhD in astronomy or a Nobel Prize. Here's a real neat picture showing Jupiter and Io. In fact, it's Jupiter I to Io. Here's a closer look at Io. Very pretty planet in a sense, colorful. It's the innermost Galilean moon. It's the most geologically active object in the solar system. It has constant volcanism going on. So constant volcanoes spewing out sulfur compounds, creating this very colorful look on its surface. In fact, if you were to look at its surface, you would find lava flows and volcanism in some parts, and right next to it would be icy snows, severe cold areas. So on one side, if you were to walk, say, along this ridge here, you could experience the heat from volcanism from the inner part of the planet, and then you could be frozen by the cold of space on the other side of the planet, or of the moon. This internal energy comes from a tug of war, a gravitational flexing that occurs between the pull of Jupiter and the pull of the moons to the outer portion of Io. So they're constantly pulling back and forth on Io, creating an internal heat that helps fuel this constant volcanism. So it's Jupiter's large tidal forces and the gravitational pull of the outer Galilean moons, especially Europa, which is the closest one to Io. No visible craters, giving Io the newest surface of all the Jovian moons, because its constant volcanism is constantly repairing the surface in a sense. So no visible craters due to the flow of molten matter on its surface. It's brightly colored due to the presence of sulfur compounds, sulfur being spewed out by the volcanoes and coming down and forming the different ices, making these beautiful colors, orange, yellow, and brown. If we were to look into the interior of Io, we would see that it's got a iron sulfide core, and maybe a rocky mantle, and that's what's being pulled back and forth, creating this volcanism. Here's a look at active volcanoes on Io. It's the first place in the solar system where volcanoes were caught in the act of being active, other than Earth. This plume here is extending 100 miles from the surface of Io. and the base would be more than several hundred miles. So you can imagine if this volcano were to erupt in Alabama, it would cover most of the state. Most of these pictures we see are from the Galileo mission that went to Jupiter. Here's a close look at one of the volcanoes on Io erupting. Here's another look, kind of from the profile view. It's easy to see these volcanoes erupting. It wouldn't be a very nice world to be on, since you have this heat from the volcanism, you have this cold from the space, you have the radiation from Jupiter because you're the closest large moon to Jupiter. So there's many ways to not survive on the moon of Io. Another look at the profile view of a volcanic eruption on Io. Europa. Europa is the second Galilean moon in the JOVIAN system, and it's very interesting. One of those moons that is interesting to exobiologists. Surface is covered with water ice with crisscross lines, so the fact that it's got water is what makes it interesting. The crisscross lines are cracks in the ice. The origin of the lines is uncertain, but it's most likely due to continued gravitational flexing causing cracks to form in the ice. It's covered with icebergs, ice wedges, and sheety ice flows over its whole surface. If we were to look to the interior of Europa, we might see again an iron or iron sulfide core, a rocky mantle, but on top of that, a very large, possibly liquid water ocean covered with a icy, very thick icy crust. The heat source for this liquid water ocean most likely would be a similar type of gravitational flexing that is going on with Europa in relation to Io, Jupiter, and the other Galilean moons. As we look further at the interior, we can see we have this very thick ice covering along with a large liquid ocean underneath. A few visible craters because it also is a surface repairing mechanism to have these to have this ice and this water sometimes surfacing through this ice. So look closer, we can see these tectonics on the surface of this ice. Very interesting grooves and patches on its surface. Almost looking like a snowplow went through here to create these grooves and these cracks. Really kind of still a mystery, but using just intuition, most likely these cracks are caused by the pulling of the ice apart by the gravitational flexing and the water ocean filling up in between, immediately freezing at the cold temperatures of the surface. Europa has an extensive saltwater ocean because Galileo has measured a magnetic field, and since it's really not really turning that fast, it's turning as it's revolving around Jupiter, so it's turning in 3.55 days, Earth days, so it really doesn't have a dynamo effect going on. So in order to have a magnetic field at all, it's very likely that the ocean we're talking about underneath this ice is a saltwater ocean. So it has ions, electric ions in it. And with the saltwater ocean then, it may possibly have life. No direct evidence of that yet, except that maybe, maybe the planet is alive. Like I said, no direct evidence of that yet. Here's a look at the surface and this terrain. This small magnetic field, possibly due to the salt water at 100 kilometers depth within the water. Don't know, but it's probably the best evidence for an underlying saltwater ocean. Here's a look at the tectonic terrain, very beautiful terrain. Similar to the Earth's Arctic Ocean, if you were to look at the Earth's Arctic Ocean, you would see similar things with cracks in the ice and patches due to melting and ice flowing coming up and creating this effect of tattered terrain. Here's some of that terrain and also evidence of a impact here. So there's a crater, and but just not totally cratered because the surface renewing itself. There was a mission planned to go and look at these moons, Europa, the icy moons, Ganymede and Callisto, and that was canceled back in 2005 due to lack of funds. The JIMO mission would have been quite interesting to try to investigate these moons that have water. And in particular, the icy moon mission in relation to Europa was going to land on Europa, use a nuclear heater to melt through the ice, no matter how thick it might be, if it might be a couple kilometers thick, and eventually release a camera into the ocean and look around and try to transmit back pictures of what was inside that ocean. Part of the problem was the idea of having a nuclear type device on a space mission, hopefully trying to get that out into space to Jupiter, but there was some concern about having that device and trying to launch it. Here's a look at the terrain and some very interesting tectonics going on here with these cracks here in this terrain. Yeah, it's like I said, some curiosity as to what might have caused that. Oh, well, maybe the constant skiing on the surface, and being such a good tourist attraction for ski lovers. Just kidding. We move on to the third Galilean moon around Jupiter, and that is Ganymede. It is the largest moon in the solar system. It's larger than the planets Mercury or the dwarf planet Pluto. Much larger than Pluto. If we were to look into the interior of Ganymede, we might find an iron sulfide core, a rocky mantle, and maybe a outer mantle comprised of water slushy material with icy crust. So possibly there is slushy saltwater type material, maybe an ocean, underneath Ganymede as well. Surface is heavily cratered. You have dark regions, which is the original icy surface, light regions of Maria of new ice. In other words, flows of water forming lava terrains or water terrains, and regions of grooves and ridges are very curious. If we look closer onto the surface, we see very nice grooves, extended grooves, and ridges and craters within those. What has caused those grooves and ridges is unknown. Here's another look at those kind of tectonics with these paths here of grooves and ridges all across the surface of Ganymede. Very interesting. A network of grooves and ridges. Has a weak magnetic field like Europa. So that's further evidence, since Ganymede is taking so long to turn, because it's turning as it revolves around the planet Jupiter. So dynamo effect not taking place again, very likely then that it has a saltwater type ocean underneath to help create ions for this magnetic field. Not likely that it has a whole lot of molten interior going on like Io. So very likely it's due to a saltwater ocean underneath the surface of the ice. Closer look at the terrain of Ganymede. Again, quite interesting. Not really know what has caused this. Here's also an interesting feature. This is probably caused by a grazing collision of a meteoric impact. Either that or one of the many large caterpillars that roam the surface of Ganymede. They're all over the place. Just kidding. No life known yet on Ganymede. Here's a beautiful picture, a more recent picture of the fourth Galilean moon, Callisto. It's the outermost Galilean moon, fraternal twin to Ganymede, most cratered body in the solar system, and has the oldest surface features in the solar system, because if you're the most cratered body, then you're showing all the different levels of cratering due to all the different time periods of the solar system, making it the oldest surface in the solar system. If we were to take Callisto and look into its interior, we would see that most likely it's just an ice-rock mixture, just a dirty snowball, one big dirty snowball, almost the size of the planet Mercury, and twice the density of water. Not differentiated like Ganymede, no plate tectonics on its surface, just a big ball of rocky ice. It does have a notable feature called Valhalla, which is a crater, meteoric impact that caused a crater, and this probably melted this icy ball and momentarily caused liquid water ice to flow, but being so cold in the outskirts of space there that those waves immediately froze in, and here you have a wavy crater type impact on the surface of Callisto. Huge impact basin with concentric ridges. Here's another look at Valhalla and the concentric ridges, the wavy, frozen impact on its surface. Here's a look at the surface of Callisto, and you can see all the varying different sizes of craters, indicating all the different ages of the solar system. The larger crater impacts, most of those occurring in the early part of the solar system, and and the smaller impacts occurring later. Here are three of the other types of moons around Jupiter: Thebe, Amalthea, and Metis. Three of the innermost Jupiter moons that actually within Jupiter's ring system, all of icy compositions. And we did the Amalthea comparison before, and it's much smaller than any of the Galilean moons. And here's where they might be located in relation to Jupiter, within Jupiter's very faint but present ring system. And these three moons are within that ring system going around Jupiter's equator. That concludes the first lecture in Chapter 8. There are 3 lectures, this one being mainly on Jupiter's moons. We will move on into the next lecture with the other Jovian moons.